control law, whether you like it or not, comes from superposition. Unfortunately, we don't teach electric circuits like this. Probably students will understand better. It gives you a much, call one fellow, take his response, call another fellow, take his response, call the third fellow, then assimilate the whole thing, create a presentation like how I have done, and then you will have a colleague like mine saying that, oh, he is speaking fantastic. So put that. But anyway, my idea of telling you about sensors is different. If you create a real-time system which interacts with the world, you will be extremely surprised to note that signal conditioning and the amount of processing that is required to tune the data is much more voluminous than the control aspect. As long as you are in a lab setup, till there you will not encounter this problem. But if you really want to make an embedded system, any system which is really interacting with the world, alright? Yeah, I give this example sometimes even to my colleagues in the industry. Right? I say, alright, and this really ends up in a very hilarious fashion. And I have seen this accident happen when I was working in National Thermal Power Corporation Limited, where we had one turbine, was around 67 megawatt rated turbine. It just came off the pedestal. It was spinning at 3000 RPM. The governor did not work, oversped. It just lifted from the pedestal and it fell 6 to 7 kilometers away. Oh. But luckily the plant area is quite large, so it didn't fall on any inhabited place. But what can happen if the data that you get, the control law was okay, but it got an erroneous data. So this is just I am impressing upon you so that you don't get carried away by the beauty of AI ML algorithms per se. What you should remember is the performance of your AI ML algorithm is only as good as your training data set, because it's not having human intelligence. You have to show it one scenario, make it respond, then show another scenario, then make it respond, and then you have to tell how it has to approximate if it sees something which it has not seen before. That's where the data becomes really, really important. I wanted to stress upon this point because many a times we take this for granted, isn't it? Many a times we just take this whole thing for granted. So data conditioning, the computations that are required for filtering out the noise from the data, the non-linearities in the sensing arrangement. So the example that I give is, suppose you are going on a flight, alright, and this I had very painfully in my career I've had to map this onto a SCADA system that we had sat and designed along with Alstom, but very painfully. So let's say you are going on an aircraft. How does the pilot know what is the height at which he is flying? How does it? तो नीचे तो नहीं देख सकता ना खिड़की इतना ऊपर हो, so he'll be using an instrument, right? एक altimeter use कर रहा है, whatever be the principle on which it works. It is showing him 30,000 feet. How do you know that data is correct? एक हनुमान चालीसा निकाल के data सही है. We cannot work like this, right? How do you know? It is showing 30,000 feet. How does the pilot know that indeed it is 30,000 feet? The more important question is, what do you do? Is there a probability that that sensor is giving an erroneous reading? Is that probability 0? It cannot be. Can that probability be 0? It cannot be. Then what to do? Yeah, sure, make it participative. People are, I don't know why participating.
So generally what happens is in flight, right? So there is this ATC and they are communicating with the number of flights in their airspace.
Correct.
So one flight will tell, like, to your 6 o'clock, there is a flight at this altitude, confirm visible something.
Correct.
And they do the exchange.
Yes, I agree with your point. You are picking on one parameter.
Correct.
On parameter by parameter, I can keep asking you the same question, and I don't think an
No, I
can
can
rattle
no
on.
answer. I'm just saying for this case there is an answer.
True.
So the only point I was trying to make is possibly multiple sensing.
Correct. You need redundancy.
Redundancy.
You need redundancy. But now the problem is, now the real fun begins. Now is when probability really starts. Now I put two sensors. One fellow is showing 3,000 feet, one fellow is showing 30,000 feet. Who is speaking the truth? That's what HODs usually encounter. Who is really beaten whom? Nobody knows. It is even more funnier now. Earlier you had only one fellow, he was lying. Now you have two fellows. Kisko believe correct?
So rationality is a question there.
Yes, rationality is a question, but when human lives are, there's a very important saying by George Bernard Shaw, no? Things in this universe are either logical or biological. He has not used the word and or on. Things in this universe are either logical or biological. और clearly बोला उसने.
Exclusivity.
But not like that.
No, that's in fact a fact.
I will not stick my neck out on that. Now you will say, अब ये आता है, then you will say, sir, even number में यही problem. दो लोग रहते हैं, झगड़ा करते हैं, मियाँ बीवी. Correct. तीसरे को लाओ अंदर. Keep the number of sensors odd. More jana. Now, two fellows are saying 30,000, one fellow is saying 3,000. How do you know those two fellows are not lying? Majority voting logic.
Only thing out here is the majority
in space application. But how do you know? Our Ibru serkundu tap heltilla anta hingu. How do you know? Can we say for 100% sure with 100% surety? Now, like this, if you go on doing, then finally that aircraft will be filled with only sensors. No space for any passenger. Correct. So when you are boarding a flight, you should always remember you are actually signing up for uncertainty. That uncertainty is covered by our faith. I am not getting into religion, I am getting into faith. All right. I am an important person in this universe. मुझे कुछ नहीं होगा. उस faith से cover करते हैं. लेकिन when you are designing an application, how do you quantify faith? That becomes difficult. My remark on this whole thing is when or if you are trying to build a real-time system, a system which really is interacting with the world, you should focus more on sensors, sources of noise in the sensors, what kind of computation is required to filter that noise, so that data integrity is assured. Once data integrity is assured, from then it becomes a easier task to design an AI/ML algorithm, then to choose whether you want to run that on the cloud or you want to run that on an edge computing device or wherever. So with that, I thought I'll give you a small example. Right? This can actually go on. This is a very interesting topic on sensor data fusion and how much of probability really works. I think we should also keep in our mind one important fact of probability. It's also lost on many people actually. In my experience, even my peers or juniors when they see them, people forget that probability just gives you the chance of occurrence. It does not tell when. It has got no temporal information. this you should keep in mind when you're working with probability. So you're working with probabilistic algorithms. It is simply giving you an averaged out, measure as t is tending to infinity. So you can't use that measure as an indicator of whether the event is likely to happen or not likely to happen in a given time frame. Remove time axis from it, then probability will work. But our mind does not think like that. We use a probability measure and we say okay. So this again, takes me back to that interesting point of Maxwell and Admiral of US Navy. Lockheed Martin had gone to the US Navy saying that we will automate your landing process on the aircraft carrier, fully automatic. They explained, it was passed through the Senate, you can read about it. So they went to the Admiral's office. Actually the chief of the armed forces there is the Admiral, unlike what is there in our country. He flatly refused. Then he was called by the Congress committee to explain why. So that I asked these guys, what is the confidence with which it will land? They said 99.999. The samples are traveling into that. Now you look at T0. So X1 has traveled through. So you can see at T0, all weights are multiplied by X1. All of it. Because this is a weight stationary architecture of systolic array. Weights are stationary, only the data is moving. In time step 2, you see now what has happened. X2 has come in, so this data gets added with this data. This data has moved vertically down, that data has moved diagonally here, so this gets added. Similar thing is happening here. Next step, X3 has come in, so these computations happen. So now you see you have computed Y1, in next you have computed Y2, and so on. Simple architecture. Alright. But the only thing is, you will have to look at proper timing and synchronization of it. Right? Because if you do not want additional protocols to kick in, then your timing and synchronization must be such that these fellows don't cause any glitches. Right? So similarly, right, you look at this. I could have done the same architecture a little different. Understand? So what I do is, there I only have multipliers, and here I have an add accumulate kind of a structure with some local memory. So now again the data comes in that direction. You see now only this multiplication is happening there. Then that comes in here. By the time that x1 has moved there, that product comes in here, so that gets added. Understanding? So here what is happening is one iteration like this, then this way, then like this, then this way, and then that add accumulates. This happens. Correct?
Why the weights are fixed?
This is a weight stationary architecture. Systolic array architectures have multiple designs. One is weight stationary. So in that multiplier, one input will always be the weight, and that will not change. Of course, that's not the only architecture. I have just taken an example of a weight stationary architecture where only the input stream is moving, the weight is remaining stationary in the processing element.
Now, what is the advantage and disadvantage if the weights are static and dynamic?
It's not a question of advantage, disadvantage. If you are having fixed weight, for example, I don't want to change the activation point. So I approximate the activation by a set of weights, alright, and only the input stream comes. So instead of having weights changing, I have a prefix, so it saves me on one clock cycle delay for changing the weight as well as for the data coming in. If my application demands like that, if both the matrices, the weight matrix as well as the input matrix is going to change, then of course I can't use this architecture. This is an architecture for a neural network where weights remain the same. Just the inputs are coming, they are getting multiplied by the weights and then passing on to the next stage of the neural network. Like that.
So in a typical control network, so forward chaining and backward chaining happens. So weights change
Oh yes,
dynamically
yes.
to enhance the accuracy
Yes.
of the specific application model.
True. This I am taking very basic structure. I am not even talking about that yet. I am just trying to explain. See, in this lecture I am only trying to explain why knock is needed. I am not explaining why a certain AI algorithm is needed, how it is good, how CNN is performing with respect to an RNN, when I should go for support vector machines. That is not what I am addressing in this lecture. But definitely we can talk about it. These are very basics like the threshold. We have a set of weights that are not changing, only the input samples are coming. This architecture can work that way. So, you can, this point I wanted to emphasize. So actually if you look at the downside of both the designs that you saw, alright, so either each element of the input must be broadcast to all the processing elements, that is the first design, or the partial outputs must be collected at the accumulator, alright. Both of this will require a bus which must scale as the size of the correlation scales. So I am arguing from this perspective, Professor. I am not arguing from AI/ML algorithm perspective. What I am trying to say is you can't use a bus-based architecture to implement this. That will be the worst thing you can do. If Google TPU uses a dedicated bus-based system. So that is why the motivation for a knock, even in such a small application, why we need the motivation for a knock. That way. So,
One of the processing elements stalls, then the equivalent
then the whole thing will stop.
yeah, that you have told. So before processing to the next processing element, I went to the output from that processing element and the input to the next processing element. So is there any mechanism where we can monitor the health of those processing elements, then give the...
But that will require buffer.
Okay. It comes with a cost.
Yeah, absolutely. No, then you put a FIFO and either at the input of everyone or at the output of everyone, or preferably both.
Is there any other mechanism which can...
As of now in hardware, no.
Okay.
In hardware, no. Because that is why I spend so much time shouting my throat for saying that data integrity is the most critical part. In the middle of the computation, you scratch your head and say, no, this data has got noise which is unacceptable. There's nothing you can do because you allowed the data to come into the PE. That is why software also, it is not that because you are making a VLSI chip, this can accelerate the computation for real-time implementation. You cannot substitute the software. That is not the idea either. So you can see this now. So here I have taken an example where both of them are moving now. The weight is also moving in one direction, the sample is also moving in another direction. Right? I can actually have a four-way movement actually, full x dash, y dash. I can have this way, all. But you can see here, see for example, in this set what is happening is inputs are moving in this direction, weights are moving in that direction. So I have just shown an instance where at time t1, x1 is already here and weight 1 has come. So you have the product w1, x1. Now slowly you can see this fellow has come here, x2, that weight has moved, w1 has moved here. So it is now w1, x2. Alright. Now then, because w1 has moved, now w2 will come, next weight has to come in this direction, correct? So now you can go on plotting this and you can see how this will work. You can have a look at that. Bidirectional movement. One direction weights, the other direction samples. Alright? So you can see how the, but in this what will happen is, the moment you get the desired result, this is one drawback in this. I have to have a mechanism to reset that, the accumulator part of that processing element. Because this should not get added to the next fellow. So this detection mechanism will have to be built so that I clear the accumulator of that processing element.
Sort of we track the size of the matrix and then we say, okay, after 3 computations they are
Correct. Or the indices.
Reset and reset will consume one cycle.
One cycle, yes.
little bit delayed.
No, I mean, the trade-off is there.
Is this okay?
You
That's why we
sacrifice
have to
time.
optimize it.
You sacrifice time.
So this design doesn't require a bus. That's my argument. Shared bus will not work. Or any global network for collecting output from the processing element. The systolic output path indicated by the broken arrow itself is n. Now, see, this guy has done a lot of research. If you want to read through systolic array architecture and design, there is a seminal paper by Kang, beautifully written. It's in ACM Transactions. You can have a look. So he proposes these kind of processing elements. So look at this. So this is a systolic array architecture where these weights remain the same, but these sums over here are allowed to change. Alright? So a systolic convolution and the cell where yi's stay and xi's and yi's move in the opposite direction systolic. So he has given you that also. Y becomes y plus w in into xn. X out, xn is directly passed to that. W out, w in is directly passed to that. So you have an architecture like this. W in comes over here, gets multiplied and added to the result over here, and this w in passes out to this. X in comes in over here, gets multiplied by the coefficient, and then gets added to what was previously in that cell, and then gets out at x out. So you can have, he has proposed, multiple processing element designs for systolic arrays. Depends upon what kind of an application you are choosing. So that's a very good paper to read. Comes paper to get the insight. So you trade off complexity of a processing element with hardware, or with area, either through utilization, throughput, or latency requirements. Correct. So now the question, can a ReRAM help? So this is some some research which we did long time back actually. Very long time back. So hopefully you are aware of a ReRAM? Somewhat. Alright. So the architecture is like this. You have input as analog. You have a DAC. Understand? So either you get a direct analog in, or if you have a digital data, convert it into analog. And you use a resistive network to fulfill superposition. Alright, that's why I was speaking about superposition so much. Alright. Superposition in this is equivalent to multiplication, correct? In this particular scenario of signals. Then you take one signal, sample it. So there is a sample and hold circuit. Then multiple such channels are there depending upon the depth that you require. Each of this is then passed to an ADC, and then you get the shift and accumulate over here. So you get a weighted sum of the product of the input signals. This is what a ReRAM does. Very, very good in implementing sigmoid functions and hyperbolic functions. Very, very efficient. Right? So can this help was the question. So you can definitely use this. There's one small thing that we did for this kind of a network. Right. So way back in 12-13. So you have a set of filters. Use that on the input activation and get the output activation. How do you pass that, on one convolution operation? So you have again a set of processing elements.